Okay, the last thing from the 4.7 notes is some application problems. The first application is an inequality type, and then the second two applications are polynomial type and a rational type using variation, which we talked about variation before in the earlier chapters, right? We did direct variation. So we're going to do direct variation again with a second degree function, and then indirect variation, which will give us a rational function. So we're going to solve and we're just going to do a couple of them. Examples here. The book does do a few, so if you look at some of the book videos, they'll do a few more examples there. All right, so the first one is a rational inequality. So I've got a ticket booth attendant. All right. So a ticket booth attendant can wait on 30 customers per hour. All right, to keep the waiting time for their customers reasonable, they make sure the line length should not exceed 8 customers on average. Right, solve the inequality to determine the rate at which the customers can arrive before the second attendant is needed. So how many customers can be in the store? All right, so that, again, between 0 to 30, because it can over an hour, right? Over an hour. So about 30 people in the store per hour. That we don't exceed 8. So where they'll have to do over, I need another person at the checkout line, so they have more people. So we want to know what rate, what X values can the customers arrive before they need to call a second person so that the wait times aren't going to exceed what they want the wait times to exceed. Keeping in mind, my X values can only be between 0 and 30, right? I can only have 30 customers per hour. Alright, so this is what we want to solve. And they gave us the equation, so you don't have to find the equation. This one we would never ask you to find the equation. So this is what we want to solve. This would be the wait times, and we want it to make sure that we keep it less than 8 on average, right? We don't want to exceed 8. And we want to know, well, what is the arrival? How many customers can arrive in order to make that happen before they need to call in a second attendee? Alright, so this is what we have to solve. And so we're going to solve this. So my first step is I'm going to move the 8 over. So I'm going to get x squared over 900 minus 30x minus 8 less than or equal to 0 is what we're going to solve. I'm going to solve it graphically. I'm going to keep this in mind for my window. Alright, a standard window actually won't work. I know that my x values have to be 0 to 30. So I make sure my window goes, so I change my x max to 30. So when I go into my window, I'm going to change my x max to 30. I'll actually pop it up and do it in the calculator. Alright, so again, first thing, make sure you're careful when you're plugging it in. So I've got my x squared divided by my 900 minus 30x. And again, make sure that's all in parentheses. And then don't forget minus 8. Then I'm going to go change my window. I know that I need to go up to at least 30, so I'm going to go to 30. Alright, I got to stay, my x value's got to stay between 0 and 30. And that's the only one I'm going to change. And I'm going to hit graph. And there's my 1, 0. Alright, that's what I want to find. I need to find my 0. And so I'm going to go to second trace, 0, so pick 2. First curve, second curve, and guess. I know I need to go over towards the end. So it's close to 30. I know the answer should be close to 30. There, I'm finally there. Oops, too far. Ah. There, finally, yes. Hit my button too many times. Alright, so the left, to the right, and then guess. So 26.967. So since we're talking customers, I'm going to round the whole customer. Right, so when I graph this, it comes up like this. I mean, somewhere over here it's going to cross. This came out 26.9. So again, we're talking people. So I'm going to round to the whole person. So I'm going to round that to 27. And so we want to know when we're less than, so we want the negative part. So if the rate at people arriving at the store is less than 27 people per hour, they don't need a second attendee. They don't need anybody else there to attend. They only need one attendee. the rate is over 27 people, then they need a second attendee. All right, so if the people coming into the store is over 27, a second attendee. Alright, so if it's 27 people or more, right, because that's the plus side. So if I'm 27 people or more, they'll need somebody else, a second person at the register. But as long as it stays less than 27, they only need one person there. And then their line's going to be... So as long as they have less than 27 people coming into the store per hour, they only need one person at the register, and they won't exceed, on average, they won't exceed 8 customers on average in line, all right, waiting to be attended to. All right, so there's an application of an inequality. All right, the next applications are going to be our direct and indirect variations. So more application. We did variations. If you go back and you look at the earlier chapters, we did variation examples. And so we're going to do more variations, but instead of just being a single x value, it's going to be an x value to a power. And for us, it's just going to be squared. We're not going to go beyond square. We're not going to cube or anything higher than that. But since it's a power, it's a polynomial type or a rational type. All right, so the first one's a polynomial variation. So if we direct vary with an n power, meaning I'm going to have a polynomial, one-term polynomial. So x and y denote two quantities. N is a positive number. If y is a directly proportional variable to some power of x, again, we're going to do squared, but y varies directly to the nth power of x, there exists a non-zero number k such that we get this direct variant variable. And so this is what the direct variant equation is. Right? Y varies directly with n to the x power, and there's some constant that's involved that we have to figure out. And I'm just going to do one example because it's just good that you're exposed to this. We're not going to do a whole bunch of examples. But we're basically, I'm just going to walk you through one example of a direct variance and one example of an indirect variance. All right, suppose that we know that the time required for a pendulum to swing back and forth. So here's my pendulum, my picture down here. So I've got my grandfather clock, and so the pendulum's here, swinging back and forth. All right, and so that's what T is that time it takes for it to swing back and forth. All right, for a pendulum, the time it takes to swing back and forth is called the period. Right, it's swinging back and forth. That's the period. So that's what the capital T is. All right, that period is proportional to the length of the pendulum. So this would be the how long the pendulum is. All right, the length of the pendulum. So the length of the pendulum, which is L, is directly proportional to the square of the time it takes the pendulum to swing back and forth. So again, it's not directed by a direct x value. It's the square of the time value. So that's what we mean by the square. And again, if it said cubed, it would directly variance by cube. We're not going to do cube. We're only going to do squared. And so what that means is the L, all right, that's the L, is directly proportional to the time it takes the pendulum to swing back and forth, but not directly. It's the square of it, the square of that time. And then it's not necessarily a perfect direct. There should be some constant k. Now, if k comes out 1, then the length of the pendulum is exactly equal to the square of the time it takes the pendulum to swing back and forth. But we don't know that. All right, so there's some unknown constant there that I have to figure out. And so that's the equation. That's the direct variant equation when it involves a square. Right? The length is directly proportional to the square of the time it takes the pendulum to swing back and forth. And so there's my direct variation equation. The difference from what we did before is the direct variation equation involved a square of my variable. Right? And it says that. It says it's the square. All right. Suppose that we know that the pendulum, so this length is 2 feet. So it's a very tall grandfather clock. And we know the time it takes to swing back and forth is 1.57 seconds. So that's the time. Find the constant of proportionality. Find the k. All right, round to the nearest hundredth. All right, so the k, well, I just plug my numbers in. So I know L is 2, T is 1.57, and I plug them in to find k. So 2 equals k times, don't forget it's 1.57 squared, right? Because it's the square of the time. You have to remember to square it. And so divide by that squared. So again, I'm just going to plug it all in at once. I'm going to take my 1.57 squared. And so k equals 2 divided by 1.57 squared, round to the nearest hundredth. And so it comes out 0.81 if I round to the hundredths place. And so there's a, there's the k. And then they ask you to use it. All right, so I know what k is. So my equation is my pendulum length is 0.81 times my time it takes the pendulum to swing squared. All right, so suppose I have a new pendulum. Suppose they make the clock bigger. All right, so they lengthen it to 5 feet. So that's the L part, right? The L part is the length of the pendulum. We want to know how long will it take for that pendulum to swing back and forth. How long will it take to complete one period to swing back and forth? We want to find time. Well, I plug the 5 in. So 5 equals 0.81 t squared. Don't forget it's t squared. That's important. All right, so again, it comes out to, and I'm going to leave it exact. I'm going to erase this and I'm going to write my work over here. And so t squared, the period it takes the pendulum to swing back and forth, is 5 divided by my 0.81. And then I've got to remember to take the square root. Since it's a positive, since it's time, I don't have to do plus or minus. Right? I know time always comes out positive. And so that's exactly what it is. And then I'll find the approximate answer. It comes out to 0.48 seconds. All right, so if I lengthen the pendulum to 5 feet from 2 feet, so when it was 2 feet, it took 1.57 seconds to swing back and forth. When I lengthened it to 5 feet, it should make sense. It's longer, it's got a bigger swing, and so now it takes 2.48 seconds. All right, the last one is the inverse variation, which means inverse means it's the reciprocal, so I divide by the variant. And I'm just going to do one example of this. So it's the same idea. Right? So if I have y and it's inversely proportional to the nth power of x, so it gives me an application of a rational function, right? This is a rational function where k is my constant and my variant, and instead of multiplying by my variable x, I divide by it. That's what the inverse part is, the division of my x value raised to some power. Right? It works the same way even if the power was 1. So it would just be x over k if it was 1. Alright, so the example, I have a distance of 3 meters and a 100 watt, I can't spit it out, bulb produces an intensity of 0.88 watts per square meter. Alright, the intensity varies inversely with the distance. So this one's a little trickier because I didn't quite spell it out like the last example. Alright, they did tell me that it varies inversely. Find the k, and then find the intensity if the distance is 2 meters. Alright, so this would be the intensity distance. The tricky part is to recognize that it's a square meter, so it's in terms of squares. Alright, and varies inversely, so it's this equation here. But it's a square meter, so I've got to remember it's squared. Right, so x is the distance. I'm sorry, x is the distance. Y is the distance. X is the intensity. Okay, so when I set this up, the intensity is a square, right? Because they told me it's a square meter. And so when we have our intensity, y is the distance 3 meters. X is the distance, or the intensity, which is 0.88 watts per square meter. And that gives it away that it's that's why we always tell you to put units on things. The units help you set up the problem. These units here are helping me set up the problem. So what I need to have is my y equals my constant divided by my square meters. And I did have it right the first time. See? Units help me out. The y is the watts per, so the y is the intensity, right, if I read it directly. Intensity varies, if I read it, intensity, so y is the intensity, x is the distance. All right, so when I set it up, all right, my y value equals my watts per square meter. X is my meters, all right, my distance, which is my meters. All right, so now I've got it set up right. So y is the intensity, x is the distance, and again, I figured that out by using my units, right? X, so I flip these around. Should be the other way. This should be x, this should be y. Y is in watts per square meter. All right, when I set up my equation, intensity directly varies inversely with distance. My units help me set up my equation. So again, I had my x and y's backwards, but once I figured out my units, I could figure out what I did wrong. All right, so it should be set up y equals k divided by x squared. The y is the watts per square meter. The x is the meters, how I get my square meter. All right, so then I plug my information in to figure out k. Alright, so the information they gave me to figure out K is my meters, my X is 3, my intensity is 0.88 watts per square meter, and so again, that goes in the Y part, 0.88 K over my 3 squared. And then I solve for K. And so I'm going to multiply by 9, right? 3 squared is 9, so multiply by 9. And so K comes out whatever 9 times 0.88 is, and so it comes out 7.92. Alright, so there's my constant, K. After I get it all set up, said and done. I may redo the video, we'll see. Right, the last thing, so once I've found K, then we ask you to use it. Determine the intensity when the distance is 2 meters. Alright, so we want to find Y, the intensity, when my distance is 2 meters. Alright, my equation is y equals k over x squared. I now know what my k is. 7.92. My meters is 2 squared, so I take my 7.92 divided by my 2 squared, and I get my intensity. It comes out 1.98 watts per square meter. Alright, which again should match up with my units. My intensity should match up with my units, right? This is my watts, and this is my square meter. Alright, and so again, my answer should match up with my units. Alright, so sorry about that one. I kind of started that one off on the wrong foot, but that can happen, and that's why units are very important, because units can help us get to the right answer. So I set up with direct variation and indirect variation, those problems are tough, and the easiest way to kind of set them up is to sort of use your units. Right? Units will get me to the right answer. And I'm not going to do a whole lot with direct variation and indirect. I probably won't put it on the test. I'll probably put it on the homework, but I probably won't put it on the test. It's just good that you're at least exposed to variation problems. Alright, so again, those are a couple of examples of variation problems, and we'll stop there. We have one section left to go. Which actually we're going to do more with power functions, right, in the last section, solving power functions and rational functions. All right, finish up 4.7.